Welcome to G Fun Facts Online. Imagine a cosmic crime scene. There's no body, no weapon, just a void where something used to be. The victim? A planet. The crime? It's been thrown out of its home, cast away from the light and warmth of its parent star, and sentenced to wander the cold, dark emptiness between the stars for eternity. This isn't science fiction. These are runaway planets, and astronomers have become cosmic detectives, piecing together clues to solve the mystery of their exile. This is the emerging field of astro-criminology. The case is wide open, and the suspects are the most powerful forces in the universe. Our first question: how big is this problem? When detectives arrive at a scene, they want to know if it's an isolated incident or part of a pattern. Well, in the case of runaway planets, it's definitely a pattern, a huge one. Our Milky Way galaxy, home to a few 100 billion stars, might be hiding a secret. It may be far more crowded with these lonely, starless worlds than it is with stars themselves. Some of the more conservative estimates suggest there are billions of these rogue planets adrift in our galaxy. But other studies, based on the frequency of events we've been able to detect, push that number into the trillions. That's a staggering thought. For every point of light you see in the night sky, there could be thousands of dark, invisible worlds silently drifting through the interstellar void. This implies that the crime of planetary ejection isn't a rare, freak accident. It's a common, almost routine part of the life and death of star systems. The galaxy is a chaotic place, and it seems that creating orphans is just part of the business of building a solar system. So if there are so many of them, the next logical question for our cosmic detectives is, what happened? What cosmic event is so powerful that it can unbind a world from its sun's gravity and fling it into the abyss? Investigators have identified three prime suspects, three main scenarios for how a planet goes rogue. The first scenario is like a violent family dispute. Picture a young, newly forming solar system. It's not the orderly, predictable system we know today. It's a crowded, chaotic nursery. Dozens, maybe hundreds of planetary embryos are zipping around, all jostling for position. In this tumultuous environment, gravitational interactions can turn deadly. Two large planets can get locked in a gravitational duel. Their orbits cross, they swing past each other, and in a massive exchange of momentum, one planet acts like a slingshot on the other. The loser of this duel gets accelerated to incredible speeds, fast enough to achieve escape velocity from the entire system. It's shot out like a cannonball, destined to never return. Computer simulations of early solar systems show this happens all the time, especially with gas giants like Jupiter, which have the gravitational muscle to throw their weight around and eject their smaller siblings. The second scenario involves an outside perpetrator, a passing star. Star systems aren't isolated islands. Our sun is constantly moving through the galaxy, and occasionally it passes relatively close to other stars. If another star were to pass through or near our solar system, its immense gravity could wreak havoc. It's like a cosmic home invader. It wouldn't even need to collide with anything. Its gravitational field alone could disrupt the delicate balance of orbits that has existed for billions of years. A planet, especially one in the outer solar system, could be gravitationally tugged by the passing star, wrenching it from its stable orbit and sending it careening into interstellar space. This stellar flyby is a powerful disruptive force, a cosmic hit and run that leaves a planetary system permanently scarred and one member short. Our third and final major scenario is a crime that originates from the heart of the system itself, the death of the parent star. For stars like our Sun, the end comes not with a bang, but with a slow, dramatic expansion. The star swells up into a red giant, engulfing its inner planets. But even for the outer planets that survive this fiery phase, the danger isn't over. After the red giant phase, The star sheds its outer layers and collapses into a small, dense remnant called a white dwarf. During this process, the star loses a significant amount of its mass. Since it's the star's mass that holds the planets in their orbits, this sudden loss of mass weakens its gravitational grip. The orbits of the remaining planets expand and can become unstable. For a planet in just the right position, this destabilization can be the final push it needs to break free from the dying star's grasp and begin its long, lonely journey. So we have our crime scenes and our prime suspects: gravitational duels, stellar flybys, and dying stars. But how do you even begin to investigate? How do you find a runaway in the first place? These planets are the ultimate cosmic fugitives. They're not orbiting a star so they don't reflect any light. They are incredibly small, cold and dark, lost in the incomprehensible blackness between stars. It's like trying to find a single piece of charcoal in a massive, dark cave from miles away. It's one of the greatest detection challenges in all of astronomy, but our astro-criminologists have developed some incredibly ingenious tools to hunt for these ghosts. The first, and perhaps most clever, is a technique called gravitational microlensing. This method comes straight from Einstein's theory of general relativity, which tells us that massive objects bend the fabric of space-time. Imagine a rogue planet drifting through space. We can't see it directly, but if it happens to pass almost perfectly in front of a much more distant star from our point of view, something amazing happens. The rogue planet's gravity, faint as it is, acts like a lens. It bends and focuses the light from the background star, causing it to briefly appear brighter. It's a cosmic magnifying glass. Astronomers monitor millions of stars every single night, looking for these characteristic, temporary brightenings. By analyzing the precise shape and duration of the brightening event, they can calculate the mass of the invisible object that caused it. And sometimes, that mass is the mass of a planet. This is how detectives find the unseen. In 2020, this very technique led to a landmark discovery. A microlensing event named OGLE 2016 BLG 1928 revealed the presence of a rogue planet with a mass similar to Earth's. An Earth-sized world, floating freely through the Milky Way, detected only by its faint gravitational influence on a distant star's light. This confirmed that even small, rocky worlds could be ejected, not just gas giants. Microlensing is a powerful tool, but it relies on a perfect chance alignment. It's like waiting for a suspect to walk directly under a single, flickering streetlight. So astronomers need another tool in their kit. That tool is direct imaging, and it works best on the youngest fugitives. While a mature rogue planet is cold and dark, a planet that has only recently been ejected is still hot. It glows with the residual heat left over from its violent formation. This glow isn't invisible light, it's in the infrared spectrum, which we perceive as heat. So to find these young runaways, you need a powerful infrared telescope, essentially a giant pair of cosmic night vision goggles. And we just happen to have the most powerful infrared telescope ever built, the James Webb Space Telescope. In a recent stunning feat of cosmic detective work, the JWST peered deep into the heart of the Orion Nebula, a bustling stellar nursery where new stars and planets are being born. And there, it didn't just find a few rogue planets. It found over 500 potential candidates. The most shocking part was that many of them were found in pairs. Binary rogue planets, two starless worlds orbiting each other as they drift through the galaxy. This discovery suggests a fourth ejection scenario. Perhaps planets are ejected from their stellar nurseries so early and so violently that they don't even have time to form a stable system. They are born into exile. Now, every good detective story has a case that defies all the usual profiles, a suspect that breaks the mold. In the world of astro-criminology, that case is an object named Che 1107-7626. At first glance, it looks like a typical rogue planet, a free-floating world with a mass somewhere between a large planet and a small star. But when astronomers from the European Southern Observatory's Very Large Telescope, and later the JWST, took a closer look, they saw something bizarre. This runaway planet is not just wandering, it's actively feeding. Che 1107 to 7626 is surrounded by a swirling disk of gas and dust, just like a young star. And it's pulling material from this disk onto itself at an incredible rate, an estimated 6 billion tons per second. This process, known as accretion, is how stars are born. They gather mass from a surrounding disk until their core becomes hot and dense enough to ignite nuclear fusion. But we've never seen this happening so clearly on a planetary mass object that's all by itself. This voracious runaway completely blurs the lines. Is it a planet that was ejected from a star system but somehow managed to take a piece of its protoplanetary disk with it? Or did it form all by itself, out in the middle of nowhere, from the collapse of a tiny gas cloud, just like a star but without enough mass to ever ignite? Is it a true failed star? Cha 1107 to 7626 is a mystery wrapped in an enigma. It challenges our fundamental definitions of what a planet is and what a star is, and it adds a whole new layer of complexity to the case of the runaway planets. This all sounds like a fascinating cosmic mystery, a great puzzle to solve. But what's the motive for this investigation? Why does it matter to us, here on Earth? The study of these lonely worlds is far more than just a cosmic whodunit. It provides crucial insights into the very origins of planetary systems, including our own. The fact that ejections are so common tells us that the early history of our solar system was likely far more violent and chaotic than we might imagine. By studying these exiled worlds, we learn about the brutal dynamics that shaped the systems that did survive. Did our solar system once have more planets? Perhaps a fifth giant planet that got thrown out in a gravitational tussle with Jupiter? Understanding the rules of this cosmic game helps us reconstruct the history of our own home. But there's another, more profound reason to hunt for these wanderers. The existence of trillions of rogue planets raises one of the biggest questions of all. Could they harbor life? At first, the idea seems absurd. A planet without a sun would be frozen, dark, and seemingly inhospitable. But it's not that simple. A large planet, especially a super-Earth several times the mass of our own world, can generate a significant amount of internal heat from the decay of radioactive elements in its core. If such a planet has a thick hydrogen atmosphere, it could act as a superb insulator, trapping that internal heat. Calculations show that this could be enough to keep the surface of the planet warm enough for liquid water to exist. Even more plausible is the idea of a subsurface ocean, like the one suspected on Jupiter's moon Europa, but on a planetary scale. Hidden beneath a thick ice shell, warmed by the planet's core, could be a global ocean of liquid water. In this dark, sunless environment, life wouldn't use photosynthesis. It would have to rely on chemosynthesis, deriving energy from chemical reactions, much like the life we see around hydrothermal vents at the bottom of Earth's oceans. While it remains highly speculative, the sheer number of rogue planets makes them a tantalizing target in the search for extraterrestrial life. If there are trillions of such worlds, the chances that some might have the right conditions for a subsurface ocean are not zero. The verdict on runaway planets is still out. The investigation is far from over. With each new discovery, with every microlensing event detected, and every infrared image captured, astronomers are gathering more clues and refining their profiles of these cosmic wanderers. The next generation of incredible observatories, like the extremely large telescope currently being built in Chile, will be crucial. They will allow us to not only detect more of these faint objects, but to study them in detail, perhaps even analyzing the atmospheres of the closest ones. The metaphorical field of astrocriminology perfectly captures the spirit of science, the relentless pursuit of evidence, the careful analysis of clues, and the unstoppable drive to solve the universe's most compelling mysteries. The case of the runaway planet proves that even in the vast dark emptiness of space, nothing is truly lost forever, not to the discerning eye of the cosmic detective.